The last topic that we're going to look at in this lecture considers boundary layers with pressure gradient. Now, there are different types of pressure gradients that can exist external to the boundary layer, and we can have zero pressure gradient, which is quite often what is studied for flat plate boundary layer flow. But you can also have conditions where there is adverse pressure gradient, where the pressure is increasing as the flow moves into it, or favorable pressure gradients, where the pressure is getting lower and lower and the flow is consequently moving more easily because the pressure is driving it into the flow. So these are the different conditions that we'll be looking at. So what we're going to do, we're going to begin looking at the x momentum equation, and we'll consider it for the different conditions. One where we have adverse, so it's difficult for the flow to move into an adverse pressure gradient, and favorable, it would be easier for the flow to move in because the pressure gradient would be driving it. So let's take a look at the x momentum equation. So here we have the x momentum equation. The terms on the left-hand side, these are the inertia force terms. And then this here is the pressure force term. And that's related to the pressure gradient. And then finally we have the viscous force terms. And so within the fluid element, all of these are in balance with one another. And what we're going to do, we're going to consider the case of looking very close to the wall, because that's where the interesting things happen when you have a boundary layer with an adverse pressure gradient. So I mentioned that we're going to look at what's going on very close to the wall. And what happens is a fluid particle moving right along the wall has to overcome whatever the pressure gradient might be. And so the fluid particle could either be accelerated if we have a favorable pressure gradient, or if we have an adverse pressure gradient, it's actually being decelerated. So in the case of an adverse pressure gradient, because that's the one that becomes quite interesting to look at, what happens is the fluid itself starts to lose momentum and it starts to slow down. It's decelerating, and you can actually get to the point where it goes to zero velocity and negative velocity. And at that point, we achieve what is called separated flow. And so the boundary layer separates. It's a very bad thing for an airfoil, for example, because that could lead to stall and then loss of lift. But for other types of flows over cylinders, we have separated flow. It happens quite often, well, all the time in bluff body flows. But what we're going to do, we're going to look at some of the logic behind what is happening, and we're going to use boundary layer equations and boundary layer theory in order to study this and understand it a little better. So what we're going to do, we're going to consider the case on the wall, so at y equals 0, and we know with the no slip, no flow condition, u and v are equal to 0. And I'm also going to say that the u prime, v prime term, which comes out of the turbulence and the turbulence stress tensor, we'll assume that to be 0 as well, which it would be. The fluctuations on the wall would have to be 0, and consequently that term would be 0. And looking back to the equation that we used a couple of segments ago when we were looking at the shear stress within the boundary layer, you'll recall that we came up with a formulation enabling us to equate the pressure gradient to what was happening in the external flow. And that's because the boundary layer cannot sustain a pressure gradient normal to the wall. And we can also equate that to the shear that is occurring along the wall. And so that can be rewritten. And so we get these equations here, and these apply whether the flow is laminar or turbulent. So what we're going to do, we're going to look at these relationships, and specifically what we will be looking at is we will be examining the first derivative of velocity with respect to y, as well as the second derivative of velocity with respect to y. And we will be doing this as well as looking at the velocity profile as a function of y and looking at how it changes under different conditions of external pressure gradient. So let's take a look at that. Okay, so looking at the equations that we just wrote out for the shear stress, for an adverse pressure gradient where we have dP with respect to x greater than 0, if we look back at our equations, we have a relationship here between dP and dx, partial or the derivative of pressure with respect to x, and on the left hand side we have the second derivative of velocity with respect to y, and so dP by dx is greater than 0 as it would be for the case of an adverse pressure gradient. We know that the second derivative of the velocity of u with respect to y has to be positive as well. But as we move out towards the outer flow region, I'll show you with some plots here in a moment, it needs to become negative at some point. And so the implication of that is whenever you have the second derivative of a function, and if it goes through 0, that is an indication of an inflection point. And consequently, we can make the statement so what that tells us is that when we're dealing with adverse pressure gradients, there will be an inflection point at some point, some location above the wall within the flow field. And where that is has implications for what is going on within the boundary layer. So what we're now going to do is we're going to take a look at a number of different velocity profiles for different types of pressure gradients. And we'll start off with favorable, and then we'll go to zero pressure gradient. So what we have here is a case of a favorable pressure gradient where dP by dx is less than 0. And this would be a case where we definitely do not have separation. And the point of inflection, if there is an inflection point, it would be within the wall. Okay, so we're now going to move on to the case where the pressure gradient is equal to 0. So moving on to the case where we have the scenario of a zero pressure gradient. In this case, there will be a point of inflection. There is no separation, so the boundary layer remains attached. And the point of inflection is at the wall. And we can see that here by looking at the second derivative term. We have a second derivative value of 0. And consequently, that's an indication that we have an inflection point. But in this case, the inflection point is right at the wall. So we've looked at the case of a favorable, a zero